You have probably experienced this minor frustration.
Just a
You
cable?
grab a sleek USB-C cable from your desk. It looks exactly like the one that came with your laptop. You plug it into your phone, expecting a rapid battery boost. Nothing happens. Or perhaps the charging icon appears, but the battery level barely moves after an hour. You swap it for another identical-looking cable, and suddenly your phone charges at lightning speed. They have the exact same shape, they have the same metallic tip, they share the same flexible plastic sleeve, yet their performance is completely different. Why does one cable work beautifully while the other feels like a useless piece of plastic? Today, we are going to unravel the mystery of the cable that promised to simplify our lives, but somehow made things more confusing. I used to think a cable was just a cable. I bought a cheap pack of USB-C cords online, thinking I had solved my tech setup once and for all. But when I tried to use one of them to connect my laptop to an external monitor, the screen remained completely black. When I tried to transfer vacation photos from my camera to my computer, the progress bar crawled so slowly it felt like dial-up internet. That is when the frustration set in. We were promised a clean, universal future, one port to rule them all. Instead, we ended up with a confusing puzzle where the pieces look identical but behave completely differently. Technology companies pushed this new standard as a cure for our messy desk drawers, but they forgot to highlight one crucial detail. The shape of the connector has almost nothing to do with what the cable can actually do inside. To understand how we ended up in this situation, we have to look back at the chaotic tech landscape of the early 2000s. Do you remember having a drawer overflowing with a tangled mess of different chargers? You had a specific gray cable for your camera. You had a different, thick black cable for your printer. You had an entirely separate proprietary charger for your mobile phone. It was an environmental nightmare. It was a daily headache. The technology industry realized they needed a unified system. They created the Universal Serial Bus, which we all know as USB. It was designed to bring order to the chaos. However, early USB designs had their own annoying limitations. We all remember the classic USB-A plug, the flat rectangular connector that we always tried to insert upside down on the first attempt. Then we had the boxy USB-B for office printers, and a whole family of mini and micro USB ports for portable gadgets. In 2014, engineers introduced a savior, the USB-C connector. It was small. It was reversible, meaning you could finally plug it in without looking. Best of all, it was designed to carry both massive amounts of power and blazing fast data. But in the rush to make one single connector do everything, manufacturers created a silent problem. They put vastly different internal technologies into the exact same physical package. You look at two identical-looking cables resting on your desk. You assume they are identical. This is the first and most common mistake we make. The physical USB-C port is merely a shell. It is the doorway, not the hallway. USB-C describes the shape of the plug, while the actual capabilities depend on the technology and the wiring hidden beneath the plastic. Inside a fully loaded USB-C cable, there are up to 24 tiny copper pins. Each pin has a designated job. Some pins send power, others transfer data. Some detect which way you plug the cable in. Cheap cables only connect a few of these pins to save manufacturing costs. High-end cables connect every single one of them. Imagine buying a budget USB-C cable at a convenience store to transfer a presentation. It takes 40 minutes because the cable is only wired to support the ancient USB 2 standard, which was designed way back in the year 2000. Think of it like a highway. A cheap charging cable is like a narrow, one-lane country road. A high-speed data cable is an 8-lane superhighway. They both have the exact same entrance ramp, but one can handle a massive rush of traffic while the other creates a frustrating bottleneck. For you, the user, this means you cannot assume a cable will transfer your files quickly just because it fits into your modern laptop. You have to look past the physical plug and verify the actual generation of the cable, such as USB 3 or USB 4. But data speed is only one part of the equation. The real danger and the real engineering magic happens when we look at how these cables handle electricity. We plug our expensive, delicate laptops into tiny phone chargers or our phones into massive laptop bricks, and we hope for the best. Have you ever wondered why our devices do not instantly fry or catch fire when we mix and match these power sources? This safety is managed by a system called USB Power Delivery, or simply PD. It is an intelligent charging standard designed to handle high wattages safely. Instead of a charger blindly pushing a high current of electricity through the wire, the charger and the device hold a quiet, digital conversation the moment they are joined. The charger asks the device how much voltage it can safely handle. The device calculates its current battery level and requests a specific amount of power. Only after this mutual agreement is made does the charger release the electricity. This process explains a very strange phenomenon you might have noticed with budget gadgets. Have you ever bought a cheap rechargeable flashlight, an electric toothbrush, or a desk toy that refused to charge using your modern USB-C to USB-C laptop charger? Yet when you dug up an old USB-A to USB-C cable, it mysteriously started charging. This happens because the budget manufacturer skipped a tiny, inexpensive resistor on the circuit board. Without that resistor, the smart charger cannot detect that a device is connected, so it refuses to send any power. It is like walking up to a silent waiter. A proper dialogue must occur for you to get your food. If you cannot speak, the waiter will not serve you because they do not know what you want. The old USB-A cable does not require a conversation, so it blindly feeds a slow stream of power to the silent device. For users, this means that if your cheap gadget refuses to charge with a high-end charger, the gadget is not broken. You simply need a basic, older-style cable to bypass the smart security check. This smart negotiation keeps us safe, but when we try to run heavy-duty power through a cable to charge a laptop, the negotiation requires an extra participant. I used to believe that a cable was a passive component, just a bundle of copper wires wrapped in a layer of colorful rubber. It felt simple. However, high-power charging requires an active system. Any USB-C cable that carries significant electrical current must contain its own tiny microchip known as an electronic marker or e-marker. This tiny chip is embedded directly inside the plastic housing of the connector plug. It acts as a digital passport. When you connect your laptop to a high-wattage charger, the system queries the cable's e-marker chip to see if the internal copper wires are thick enough to handle the massive heat generated by high currents. Consider this situation. You connect a modern laptop to a powerful 100-watt wall plug using a random, unmarked USB-C cable you found at the bottom of a drawer. The laptop charges, but it does so incredibly slowly. Even though both the charger and the laptop are capable of rapid speeds, the charger limits the power output to a safe level because it cannot find an e-marker chip telling it that the cable can handle the heat. Imagine a security guard stationed at the entrance of a weight-restricted bridge. Even if a heavy cargo truck wants to cross, the guard will block it unless the driver can produce a certified manifest proving the vehicle is safe for the bridge. The e-marker is that certified manifest. For you, this means that if you want to charge your power-hungry devices at maximum speed, you must look for cables labeled for high-wattage delivery, such as 100 watts or 240 watts. Charging your devices quickly is a great convenience, but what happens when you want to use that same cable to run a high-resolution display? We all dream of having a clean workspace. A single cable that charges your laptop, connects your external hard drive, and displays your desktop onto a beautiful 4K monitor. This dream is possible, but it requires elite protocols known as USB 4 and Thunderbolt. These technologies represent the peak of what the USB-C connector can achieve. They work by combining massive data bandwidth with maximum power delivery. Instead of separating your video signals, data transfers, and power into different cords, these standards bundle everything into a single, high-speed stream. If you connect a high-speed external solid-state drive to a Thunderbolt port, you can copy a massive movie file in just a couple of seconds. If you try the same task with a basic charging cable, you might find yourself waiting for several minutes. It is like comparing a high-speed passenger train to a local freight train. They both run on steel tracks of the exact same width, but the high-speed train has specialized cars and priority access to travel at incredible speeds. For the user, this means that if you are building a professional workspace with multiple monitors and fast storage, you should invest in cables officially certified for USB 4 or Thunderbolt. They cost more, but they are the closest thing to a truly universal cable. However, this incredible performance comes with a physical limitation that many people do not realize until they try to rearrange their desk. You might think that if a USB 4 or Thunderbolt cable is so capable, you should just buy a very long one. A 3-meter cable would let you sit comfortably on the couch while keeping your super-fast connections intact. Unfortunately, physics has other plans. High-speed electrical signals do not travel well over long distances. As data speeds increase, the electrical signals traveling through the copper wires become highly sensitive to degradation and external interference. The longer the copper wire, the more the signal fades, leading to data errors and dropped connections. If you try to run a high-definition monitor using a very long, cheap cable, you will likely experience flickering screens, static, or no signal at all. To keep speeds high, manufacturers have to keep the copper lines incredibly short. It is like trying to have a conversation with a friend. If they are standing right next to you, they can hear your whisper. If they walk 50 yards away, you have to yell and they will still struggle to understand your words over the ambient wind. For you, this means that high-performance USB 4 and Thunderbolt cables are usually very short, often less than 1 meter. If you see an exceptionally long cable advertised with high speeds at a very low price, you should be skeptical. To get high speeds over long distances, you need expensive active cables that contain built-in signal boosters to keep the data clear. When USB-C was first announced, we were told it would solve our cable clutter. We were told we could finally throw away our old boxes of miscellaneous cords. But here is the irony. In trying to eliminate physical clutter, we actually created a worse, invisible kind of clutter. I realized that the simplicity of USB-C is a design illusion. By standardizing the physical shape of the connector, we hid all the complexity inside the cable. In the past, if a cable did not fit into a port, you knew instantly that it would not work. The physical shape gave you a clear answer. Today, the cable fits perfectly. The plug clicks into place with a satisfying snap. But behind that snap lies a silent gamble of compatible protocols, power ratings, and data generations. We traded a drawer of different-shaped cables for a drawer of identical-looking cables that all do completely different things. Navigating this situation does not require a degree in computer engineering. You can manage this with a few simple habits. First, do not throw away your old USB-A to USB-C cables. They are highly useful for charging simple devices like wireless headphones, electric toothbrushes, and budget smart home gadgets that do not understand modern power negotiation. Second, start labeling your cables. When you buy a high-quality cable that supports fast charging or high-speed data, wrap a small piece of colored tape or a label around the connector. Mark it with a simple letter like P for power or D for data. This simple step ensures you will not grab a slow charging cable when you are trying to back up your files. Third, when buying a new cable, look past the brand name and focus on the certifications. Look for the official USB-IF logos or Thunderbolt symbols printed on the packaging. These symbols tell you the exact speed and wattage the cable is certified to handle. What surprised me the most when looking into this technology was how much engineering is hidden inside a simple cord. We interact with these cables every single day, plugging them into our phones and computers without a second thought. We expect them to work quietly in the background. It is easy to take them for granted. But beneath that simple plastic sleeve is a delicate ecosystem of microchips, copper lanes, and safety protocols. The transition to USB-C was not just about making a plug that works in both directions. It was about creating an intelligent bridge that can handle our modern digital lives. We just have to be a little smarter about which bridge we choose to use. If you enjoy technology stories explained in a simple and engaging way like this, don't forget to like, subscribe, and turn on notifications so you won't miss future videos. Every week, we'll explore familiar technologies that hide fascinating truths most people have never noticed.